You know, I don't understand why I put all this effort into coming up with these hilarious intros when I'm just going to walk into class and there's just going to be a bunch of, oh, was there a video? Oh, I didn't watch that. Why do you even think you're funny? You're just so lame. I mean, what do they expect of me? I teach math. Whatever, let's just get this over with. Hi, I'm so glad you're here. We're gonna keep talking about probability, and I want you to recall that last video we talked about the total law of probability. And the total law of probability says if you have events A and B, that you can write the probability of A as the probability of B times the probability of A given B plus the probability of not B times the probability of A given not B. Right? And we talked through this scenario about your vacation to New York to go to the National Museum of Mathematics, or MoMath, right? And we said that your decision-making tree followed this probability tree, right? That we were hoping to save $500 by the end of the semester to be able to go on our trip. And we said that the likelihood of saving that $500 was 0.6. So that gave us a likelihood of not saving the $500 is 0.4. And if we did save our $500, then it was really likely we were going to be able to go on our trip. 90% chance we were going to go to MoMath. But there was still a 10% chance that something would happen, that even though we had the $500, there's just circumstances that happen and we don't get to go. Similarly, even if we don't make it all the way to our $500, maybe we get close enough that we can make things work. So there's still a 30% chance that we get to go, but a 75% chance that we don't. And we talked through how this first decision, these are actual probabilities. This is 0.6 is the probability of S, and this 0.4 is the probability of not S. But all of the second line of branches are conditionals. This is the probability of M given S, and this is the probability of not M given S. And this is the probability of M given not S, and this is the probability of not M given not S. And we use the total law of probability to say, well, if we know all of these conditionals, can we answer the question of what is the probability that we get to go to MoMath? And we said that that was the probability of us savings times the probability of going to MoMath given that we saved, plus the probability of us not saving, times the probability of us going to MoMath given that we did not save our $500. Now, I want to flip the probability a little bit and ask, what if at the end of the semester, a friend of yours is scrolling through Instagram or whatever the current social media trend is? Who knows how long I'll keep using these videos before I update them. But say that they see pictures of you from the National Museum of MoMath. So at that point, they're pretty confident that you're not just photoshopping that together, that you actually went to MoMath. And what if they want to ask the question of, were you able to save $500? Right, what if we want to ask the question of, what is the probability that you saved $500 given that you went to MoMath? Right, so it's another conditional, but the difference here is that we've switched the order. Right? We have a bunch of conditional probabilities, but they're about the probability of going to MoMath based on whether or not we saved. We want to ask, how can we answer the question of, what's the probability that we saved $500 given that we did go to MoMath? Right? Because there is a path through this decision tree where we get to go to MoMath even if we don't save our $500. So the fact that we're there does not guarantee that we saved $500. So let's think about this. So the first thing that we can do is we can use the definition of a conditional probability to say that this is the probability of S and M divided by the probability of M. But the probability of S and M, right? We have formulas for that as well. We have the general multiplication rule that says that we can rewrite an AND statement as a statement involving conditional probabilities. So one way that we could rewrite the probability of S and M is the probability of M times the probability of S given M. But we don't know the probability of S given M. But we can also rewrite it in terms of the other type of conditional. So we can write this as the probability of S times the probability of M given S. And then we still need to divide by the probability of M. But these probabilities are probabilities that we know. They're the probabilities from the tree. And we know the probability of M, right? We have it here from the total law of probability. So that gives us the formula of the probability that we were able to save $500 given that we went to MoMath is the probability of S times the probability of M given S divided by the probability of S times the probability of M given S plus the probability of not S times the probability of M given not S. And all of these probabilities we can read off of this probability tree. So this is equal to 0.6 times 0.9 divided by 0.6 times 0.9. You'll notice that this is the same statement as here. This is always going to happen. Plus the probability of not S, so that's 0.4, times the probability of M given not S, so that's 0.3. And so this becomes 0.72 divided by 0.72 plus 0.12, which gives us 0.72 divided by 0.84 for a final answer of 0.857. So if you went to MoMath, the probability that you are able to save your $500 is a little more than 85%. And this formula for turning the conditional probabilities around, this part right here, is known as Bayes' theorem. Not to be confused with Bayes' theorem, the hottest new gift for that special someone in your life. I don't know what to say. I guess we're done.